of Engineers Without Borders Society this year. What do? We try to promote globally responsible engineering in future engineers. We do that on campus through one-off events such as this and our Designathon or the Green Careers Fair we hosted. We run projects. Well, in normal years we run projects, and we also do outreach sessions in local schools. So there are lots of ways to get involved. That's a bit of a brief intro. I'll put some links as to how you can sort of further your involvement in the chat. And if you have any questions, then you're welcome to get in contact with me. I'll put how you can do that in the chat as well. So, moving on. Today we are here to hear John talk about climate resilient homes, and I will let John introduce himself and take it away.
Well, hi everybody. Thank you for inviting me, Nathan. Yeah, so this is a half an hour you're never going to get back. So I'm a senior lecturer at Sheffield Hallam University, as well as being a bit of an activist and sort of general environmental enthusiast with a number of groups across the city. I suppose most notably working towards zero carbon Sheffield by 2030 with Sheffield City Council. I'm one of their technical advisors with regards to strategies for reducing carbon on that one. It's called the Green City Partnership Board. So that's me sort of promoting myself. I've been teaching for just over 20 years. I started off, would you believe, in town planning, but my I've sort of qualified in more into the construction side over my 20 years there, starting with renewable energy and then sort of moved into resilient construction. So although I've been in the climate change sort of debate since the 80s, I've never I've never questioned the science. With me, it's always been about, right, so what should we do about it? Being a Yorkshireman, of course, I've always assumed the worst. So whenever, you know, I always hope for the best, but assume the worst. So when I was looking at how do we respond to what possibly comes in, to me, the worst case scenario is about a 4-degree temperature rise, which is definitely on the curves. And so I've thrown together my 20 years of experience with regards to building design, and I pulled it all together for a retirement plan for me, which so the plan is that I build this house for me or a client if somebody comes to me before I get to do that, because raising the cash is proving challenging. But I have a site location and an idea, and the concept to it was always around the £200,000 mark for a £200,000 mark for the house all in. So that's the kind of scale of money. Kath. So it was around a £200,000 range for the house and the land, which is why I headed up north, because the only place I could find a large enough plot of land for what I'm looking at for this kind of grand experiment has been Scotland. And then I went up to Scotland, and then he went even further north when I discovered how beautiful it was and sort of legged it over there. So this is my presentation. I will share my screen. Hopefully everyone can kind of see this. You got. Can you? No, you can't. Can you see that? No, Nathan? Yeah, you can see the slide. Right. Okay. Right. It's an odd platform. It's my first time on this kind of platform, so please forgive me with regards to that. So those are my contact details. You're best using email. At the moment with COVID and everything, my work phone is just a massive answering machine. But feel free to email me. That's fine. And the NBE is my department, Natural and Built Environment. So yeah, let's jump into this. So here we are in 2020, and this is our carbon reduction curve requirement. So if we're going to meet the 2050 target, and I don't know about you, but you know, as much as I wish that humans are capable of great things, I find it an extraordinary curve that for us to actually follow that. And when people say, "Oh, it's all right, John, we've had COVID, that's reduced our carbon emissions," well, actually, it's only reduced our carbon emissions by about 10% for 2020. And so, if you imagine a brick of carbon being produced since 1750, then you know our 2020 brick is 10% smaller. And we're pretty confident now that extreme weather events are, in some calculations, 30 times more likely in the UK. Heavy rainfall events are 30 times more likely. The hot and cold events slightly less, but you know, engineering has a solution here. So this is the one house that survived Hurricane Ike because they'd sprung for the sustainable options, the resilience options on their house. I found it the most extraordinary picture. You know, that's what they were kind of talking about. That, you know, and you know, it's not rocket science. Everything I'm about to talk about today is is already developed. There's nothing novel. Now, Sheffield, sorry, not Sheffield, the government has proposed this as our 2030s house. And I find this sort of appallingly embarrassing. Oh, sorry. Appallingly embarrassing in that we've already surpassed this in every way, arguably 20 years ago. So this is their house for 10 years from now. But 26 years ago, the first autonomous house that I'm aware of in the UK in Southall, in Nottinghamshire, was built by the Robert and Barbara Vale. And this was autonomous in energy and water, not food, but highly insulated. And they, 6 years later, built these at Hockington nearby, which actually, a bad year, get this, a bad year is 30 quid on utilities. So this is a bungalow, earth sheltered, linear layout, so all the rooms face south, with a sun space that keeps it warm, and they have no primary heating source in there, just an insulated concrete box that uses the sun and ambient heat capture from uses within the building. And I've been following this for 20 years. I was actually involved in it, not in the construction, because that was the Vales, and it was a self-build, but I was involved in the renewable energy system. So I helped them with their wind turbines because they were having problems getting it through council. Interestingly, they've got 2 wind turbines, both of them 20 kilowatt, very small turbines. And the first one was refused by the council, and I helped them with the appeal. And when it went up, everybody saw the wind turbines and went, "Oh, literally, is that it?" And the second wind turbine went through without a single letter of concern. So, you know, interesting that when people know what's coming, this fear of the unknown was what was the concern there. But, you know, it was really good for me because I got involved with that. So I've been taking students to see these houses. So it's a terrace of 5 houses, this one. And I've used this as a model for my house to a greater or lesser extent. But I put more resilience elements in that. So it's a terrace of 5 houses, and they were built on the same price, about 80k a house. So these aren't ludicrously expensive. These were built for what is currently a low-end 2-3 bedroom house built by a volume house builder. So self-build would be more than that now, but for volume house building, 80 to 100k is around sort of standard build cost. So these are pretty standard, but zero heating, and they've got PV and wind turbines that work as a hybrid system. So like I said, on a good year, they'll get 50 quid back from the utilities, and on a bad year, they might pay 30 quid on their utilities. So they're reasonably close to zero carbon, as well as producing about 50% of their own food within what is quite a large plot of land that all 5 houses sit within. But yeah, So switching to my house, it's about as far north as you can get, Wick. So it's about half an hour from John O'Groats, heading north from there. It's a great location, although not the most inspiring on the east coast. The reason I picked it was that the road's to the south of the plot, which means you can't build anything that will shade me, which was part of the design. And there's a burn, as they're called up there. Excuse my Scottish accent, I don't have one. Which has got fresh water, which feeds into the local whiskey distillery. So it's good. It's good enough for them. It's good enough for me. Is kind of the logic to that. But quite a large site at almost a hectare, and only 30k. But don't share that. So I could repeat this. But it's a public road on there and everything, and adjacent to the oldest castle in Scotland, would you believe? Which is it's the most boring castle. That's why nobody's ever heard of it. It's a really boring little brick square. But yeah, so historical, and the fact that this house sits on a concrete raft made simplified matters with regards to digging that. So no significant foundation. So this is the design as it stands. So it's kind of a keyhole footprint. The main building is the circular building, and there's all sorts of reasons why I went circular rather than standard square plot, even though it added about 5 to 8% to the price. But I'm using insulated concrete formwork, which you'll see in a moment, which actually isn't as expensive to build curved walls as it is with brick and block. And you get some huge advantages in terms of structural strength. So part of the resilience element of this is that it's flood-proof to the lower windowsill of the main circular house. And if you build a house that is tanked, as it's called, so like an inverse swimming pool, and it's square, you have to really reinforce the walls on a square house because they buckle. Whereas a circular house, just because of the nature of the circle, passes that energy around it, and they're much stronger to that. So the research by BRE, in their flood tank, they built actual buildings and flood them up to a meter and a half. They've been easily been able to build buildings that are structurally and waterproof capable, but they crack over time. And so a lot isn't talked about that. So actually they've got strategies for letting the water in to equalize the pressure. I wasn't comfortable with that. So so that's the main house. Interestingly, or well, I find it interesting, it's an upside down house. So the bedrooms are downstairs, the living rooms are upstairs. Another flood resilient strategy. This is my opinion. Any house that has a risk of flooding should flip their houses, because it tends to be that your lower cost, lower impact, flood damaged items are in your bedrooms, or you can grab hold of clothes and blankets and mattresses and drag them up the stairs. Whereas a chest freezer is a little more of a challenge taking up the stairs. So, having that inverted house gives you a nice view, which was another thing. You could see the sea on this house. You'll be able to see the sea, but it makes it flood resilient. And there's a thermal performance advantage, since you tend to like it cooler where you sleep, and you tend to like it warmer where you sit in the sedentary fashion. If you flip the house, you've generally got a warmer upper floor, which will save you probably around 10% on your heating. Not a massive amount, but every little counts. And then the round walls again, they offer much lower heat loss. It tends, if you look at the profiles for heat losses from a standard square house, again, it's the corners that actually lose far more heat than the actual flat walls. It's something to do with it is to do with the pressure differential on the corner, and the fact that on the corner your insulation doesn't work as well. So there's another reason why, if you've got the space, you go with a curved wall. And like I said, this is called insulated concrete formwork, and it comes out like giant Lego bricks, and you build it, by hand, and you build it by hand, and then you pump concrete into the core of it. And so it's an incredibly fast build process. Now, if anybody ever built in Scotland, they will understand why. Not only is this structural element really important, and the fact that you can extrude the insulating, it looks like polystyrene, it's not, but it looks like polystyrene. You can extrude it in any angle, even in a curve. It makes a curved structure much easier. But you can also throw the walls and put the roof on within 2 weeks. And in Scotland, that is really, really important on a build, that you're then working internally from that point onwards. So, you know, that was a key part to this, as well as the opportunity of what we're doing with this, is that you can strap on external insulating material. So you can take the U value down to 0.3, U value of 0.3, which is about 10 times better than the standard for a wall performance. But one of the more interesting elements of using insulated concrete formwork is that you can cast the floor and up the wall all the way to the lower window sills in a single pour. So you do that in a single pour. And when you do that, and then what happens is that the door into this area is actually elevated by about 4 steps. So you walk down into the ground floor. So the bottom door of the door, which is inside that entrance foyer, you walk in and then you walk down three or 4 steps, depending on what the depth of the steps are. I haven't quite decided on that yet. To the ground floor. And what that means is that you can literally take the water flood levels up to the windowsill, and the water won't come in. And it can't come in because you've cast a cup, for all intensive purposes, in a single pour. And it costs no more to do this. I find it extraordinary that this isn't just a standard strategy that is employed in any location that's on a floodplain, has a reasonable risk of flooding. Because, you know, yes, it's 4 steps up and then 4 steps down, but what you've got there is about a meter of give in terms of the flooding. And that if you look at the statistics on what most houses get flooded by, it isn't up to the second floor window, although that does happen. It tends to be 300 mil to about the 300 mil to 600 mil flood level. So if you go up to 1,000 mil, you've kind of made that building resilient to most floods, you know. So let's say, and then the house uses thermal mass just like the Hockington houses that I showed you before. So the game is that no matter what the external temperature is doing, the internal temperature remains relatively level. But the walls are actually insulated inside and out. So you're not using the thermal mass of the external walls. Excuse me. They're just structural. They're just structural. Interestingly, the ground floor walls are built, it's almost like the wrong way around, out of super heavy brick blocks. So the internal walls between the rooms are made of heavy concrete blocks, or as heavy a material as I can get away with. I was looking at rammed earth and stuff, and I'd like to look at that, but you know, I was going with cheap, I'm afraid, and it's much easier building, and especially when your brickies working indoors. So remember, you know, you've got that in Scotland as well. So it's all turned around with that, and then also I'm stealing from the Romans and going with a hypercaust underneath the floor of this building. So what we're doing here is pushing warm air underneath the floor, where you've got about 300 mil. You've got about 300 mil of concrete below and 300 mil concrete above, and so that floor becomes the entire building's radiator as you work it out. So by my calculations, that should stabilize the temperature no matter what it's doing outside, because you've got an ultra low U value, so gaining heat or losing heat externally. The windows are shuttered, which we'll show you in a moment. So you can get away with that. And then what you're doing is what I want to do is using a mechanical ventilation and heat recovery. So you draw the air out of the building. Sorry, you draw the air out of the building and vent it, but you capture the heat from that air, and then you push that under the floor. You push it under the floor in the middle of the floor of the circle, and then the air just moves to the edge of outwards from the center where it vents. And this building, I've been really decadent. It's actually got a service riser. So there's actually a 2-story high room where all the services come in and are distributed around the house. And what it means is that the electrics, water, plumbing, they're all external in the building. I expect it to take a day and a half, 2 days to put it all in across the building. And they're all exposed, which are then covered by ducting at ground level, and that doubles as a seat all the way around the perimeter of the house, but also storage. So it's about doubling it up. My wife said there better not be a shortage of storage. I've seen modern houses, and so there's a vast amount of storage in there, but all the pipe work, all the electrics are all exposed, so you can keep them secure and do the maintenance. It is a house for an aging person, as I am or will be, and so I wanted the maintenance to be very, very simple. I'm a great believer in the keep it simple, stupid KISS principle for the design of things. And so all the plumbing's external in the void. So all the toilets are against the riser. And so all their cisterns, all the water supply, the plumbing, the dishwasher, the washing machine is all in the riser as well. So all the water is all kept in there. And so if you've got a flood, it's all contained in that room as well. So it kind of manages that as well as dealing with it. Now the windows, they're quite interesting. I stole this one from Canada. That they're all recessed, and so the ground floor windows, I've gone cheap. It's only double glazed, because what I want to do is let heat in when there's heat to be had. And people don't often miss this point, that if you put a triple glazed window in, yes, it keeps the heat in, but it also stops sunlight from entering the building. Every pane of glass, you'll lose about 10% of the potential insolation gain of the building. So I kept it double glazed and recessed the windows and put a really very efficient shutter around the ground floor. Remember, this is upside down. So these are your bedrooms on the ground floor. So closing the shutters at night shouldn't be a problem, and then holds the heat in the building. And then the upper floors, that's where I've sprung a bit extra. So there it is triple glazed, and they don't lose heat as much. So it's this idea of having this lower and upper floor treatment, but the windows will perform as good as the walls when you do it. The roof, moving on to the roof, is just a single cast concrete unit. I know it sounds kind of crazy, but it's a single unit. By my calculations, it's about 12 ton. So that ain't blowing off. It's my water collection location as well. So I've got a coating that is designed for rainwater collection for potable water. So you paint it over the top. It's got a 50-year lifetime associated with it. And so you get no leachate out of the concrete, which is a bit, I mean, you can put waterproof additives into concrete. And so generally I've seen people collect rainwater off concrete, but I'm this is my home. So I went for that. It looks like a copper roof as well. Not that, it's got that green color to it when you painted it. So my rainwater will be collected off this roof, as well as it acting as well, by my calculations, when it's tied down the way I want to, it's category 5 hurricane strength. So so you've got thermal performance down to -20 up to +40. You've got a wind resilience with the circular structure and the roof up to category 5 hurricanes for the main part of the building. The rest of the buildings are quite low, so I'm hoping they'd be able to duck that. So again, we're working. So I've been talking about flooding, but there are other climatic elements. And then the fact that it's got a cone roof, I've decided to take this PhD research, which was this Aluian, I don't know how you say it, a wind turbine integrated roof, which was quite interesting. And the idea is that you've got a vertical axis turbine, And the logic is that it negates the turbulence that you normally get off a roof. So the roof overhangs quite significantly so that you don't overheat the building, but you can still leave the windows unshuttered, which is kind of important. So in the summer, the roof shades the upper floor so you don't overheat. But this also gives you a larger capture area or a turbulence area, which will flatten or get rid of that turbulence. So this vertical axis wind turbine should work as well as it would on the top of a big stick, on the top of a tower. I'd hoped that it would actually. I did some research about 10 years ago where we had a wedge-shaped building, and the wind blowing up the wedge actually improved the performance of the turbine actually 3 or 4 times. And I was really excited when I got a cone roof, and I thought, oh, this is it. I'm going to get 3 or 4 times the output. And of course, you know as well as I do that when the wind blows over a cone like that, the wind slips either side of the turbine, annoyingly, and doesn't get concentrated over the eave, over the ridge, I mean. So, so on a ridge, it works really well. On a cone, it doesn't. But what it does do is kill the turbulence. So you get a laminar flow over this roof, which so I'm quite hopeful about that. And the turbine itself is called Windside. It comes out of Denmark, Finland. They argue that they are the most resilient wind turbine on the planet. The picture on the right there is of an Antarctic survey data collection unit where they claim that their turbines can withstand 300 to 400 mile an hour winds and just keep on going and just keep producing power, which made me interested, and it's partly because it's maglev. The magnets are not actually in contact with the electric motor. They just spin above it and they're hovered there. So you don't get any noise to speak of either, just the blade wind noise. But remember, again, I put the wind turbine on the roof, but you've got the living space on the roof. So even if you did get some vibration and noise from that vibration, that's where you're awake and you go downstairs to the ground floor for sleeping. So it's my hope that any kind of problems associated with that you might get from a wind turbine integrated into a building will be negated. And I'm hopefully going to get, well, no, I will be putting some dampers in there to stop that. I haven't talked a lot about the keyhole element to it, but the greenhouse has got solar panels integrated into the roof. So we're dealing with Scotland here. So the summer, the sun's very high, and so it would overheat the greenhouse. So I've got solar panels integrated so it shades the greenhouse. But in the winter, when I'm looking to maximize greenhouse output, then the front facing element of it, the sun comes in from that. And it is my belief that I'll be able to grow 365 days of the year using that. And one of my PhD research is actually in a method of growing without soil called aquaponics, which uses fish and plants as a closed cycle food production. And as such, the plants in the greenhouse have no soil, but they're fed from, and this is, you'll laugh now, so there's a freshwater swimming pool in there. So my wife calls it a freshwater swimming pool. I call it a thermal, oh my goodness, sorry, I've got this thing on a timer that just supposed to keep me in time, but I'm obviously speaking too slowly. So it's a freshwater swimming pool developed by a Somerset company about 5 or 6 years ago. Oh no, it must be about, oh God, it's about 10 years ago. So freshwater, normally you get an algae problem with that. They've come out with a really interesting solution in that they use a biofilter to pull the phosphorus out of the water, which means that you get very low algal growth in there. But this water is technically potable, although I have a separate potable supply. But what I'm doing with this one is that this is a settling. This is so this will heat up through the summer, and it will act as a thermal store for the rest of the house. So it acts as a thermal store. It is a swimming pool. It's 10 meters by 3 meters swimming pool. But also I have fish tanks all the way around it, and then the fish poo water goes out of them through the plants, gets cleaned by the plants, and then is returned to this swimming pool clean, and then gets pumped back into the fish. And that's the cycle. So it produces my food, it levels my temperature, and supplies me with all my non-potable water for the house. And it's designed in a way that you would let me show you this. It's designed in a way that once the level reaches once the level reaches 1 meter deep at the deepest point, you're not allowed to swim in it anymore. It just becomes a water store. But so you can visualize how much water you're actually using as a household. You use too much, you lose your pool. You're not going to run out of water because there's still quite a lot of water left in the pool, but you've lost that leisure activity. And my thoughts, because I had teenage children when I was designing this, was like, how do I make them see how much water they are using? And the way you do that, of course, is to have an open air store. And the more you use, the lower the pool goes down and the less chance you have of swimming in it. So that was my kind of logic to that. Water treatment for the non-potable store uses a well-used sand filter technique. So it's rainwater through a 1 meter sand filter, which has been used for 20 years at Hockington for non-potable water and works fine in a UK climate. A little more challenging in hotter climates, but where it's reasonably cool, you don't get the bacterial element, and the what's it called, the schmutzdecker layer that forms on the top of the sand is enough to keep it safe for UK non-potable uses. So dishwasher, washing machine, shower, all that kind of stuff. It meets World Health Organization clarity, and it's incredibly simple. And the actual potable water I'm sending through a standard three stage one of string filter, carbon filter, and UV filter for drinking, which is off the shelf and about 300 quid a year to maintain. So my potable water goes through that, and my non-potable water is kept in this fresh water. Oh, by the way, so it's heated, yeah? And I did make that clear that but unfortunately, by my calculations, around February, March time, before the sun starts coming out again, temperatures would get quite cool in the pool, so you'd probably have to use a wetsuit. So again, it's a trade-off. It's not a heated pool, even though I am intending to heat it through the summer using standard evacuated tube solar collectors. So the temperature at the end of the summer would be quite warm, and it's a super insulated kind of room, that is. So the idea is that it would be inter-seasonal heating, and you'd move the heat as required from the pool room into the main building using your ventilation system. So if you don't need the heat, you just vent the heat. But in the sort of deep winter, you might strip the heat from the pool room into the house. So again, you've got no primary heating system. I put a wood burner in there because it just makes me feel safe, and also that's what you'd need if you're getting down to below -5, -8. You might need some additional heating in there. So UK temperature, probably not. My sister-in-law, she lives in Alaska. We did some profiling of a eco house over there, and they had a wood burner, and I modelled that on that, and that remained kept the house at 18 degrees through a -30 winter in Fairbanks, Alaska. So I'm reasonably confident about the low temperature ratings. It's the upper temperature stuff that I'm slightly less. I've not tested that, even though the numbers come out with that. So that's me done. That's really, I'm sorry it was so fast. You can maybe look at the video recording and play it at normal speed if you want to understand what I'm talking about. But I'm open for questions if anybody's got any, and any thoughts around that. But be gentle, it's my dream.
That was really interesting. Thanks, John. As John said, the talk has been recorded, so you'll be able to access it again via our website. I'll just pop the link to that in the chat. anyone has any questions, you're more than welcome to put your camera on, turn your microphone on, and ask them.
And there's not a lot of stuff here, is there? We can have a chat,
or you can pop them in the chat.
Oh, where is the chat? Like, I don't know. Where do I find that?
If you go to the top right, then there's like a little message box. At least if it's full screen.
Yeah, there it is. Okay, there we go. I've got it there.
Yeah, take it away.
I'm sorry if I missed this. I had a bit of trouble getting in because my internet wasn't cooperating. But have you ever thought of using alternative materials to normal cement in concrete?
That's a fantastic question, and yes, I have. My materials guy at my university has been hard selling the low carbon absorption concrete that he's recently become aware of. I think it uses steel blast furnace ash for aggregate rather than the normal one. And you know, if it meets the strength requirements, we were also looking at putting additives that react with the concrete when it's setting and create tiny CO2 bubbles in the concrete as well, for the wall concrete, which lightens it up and weirdly strengthens it because it's then full of holes, but also reduces its thermal conductivity as well. So I was seriously looking at sort of low combat bubbly concrete, but you can't do that in the basement and the flood, that first cast bit, because we want that as strong as it possibly could be. And there is this concern when you're looking at a tanked cup like that you have to put enough weight on top of it, because if you've got the water around the outside in an extreme flood event, you get situations where concrete pools will rip themselves out of the ground because they're lighter than the water around them. So yeah, we wanted to keep the weight up weirdly. But yeah. So low carbon concrete. I know it was a real challenge for me, which is why I was looking at rammed earth internal walls, maybe that are stucco for the high thermal mass internal, which would make me feel a little bit better if I had the time and resources to do rammed earth. I mean, it looks, I don't know if anybody's ever seen rammed earth done properly, but it looks like sand. Well, it is sandstone, and you can do slightly different coloured sand as you layer it out, and then when you can buff it up to an absolute mirror finish. And I would just love that on all my internal walls on the ground floor, and it would have a huge thermal mass as well, and have a virtually zero carbon kind of thing. Although considering the local area, I'd have to import the material that I'd be ramming, which makes it damnably expensive, unfortunately, because ideally you'd use the local material, but this area has got virtually no soil at all. It's a exclaciated area. The soil depth down to concrete down to granite is only about 600 mil. So I mean, it's a great location for putting you don't need foundations or anything. You could build 300 stories on this concrete, which it's close to the coast. And that was one of my things. I was a bit twitchy about that until I got the geological survey and realized the coastline hasn't moved for about 1,000 years. So, I'm kind of confident with that. Anyway, sorry, that isn't your question. Yes, simple answer. I could have answered that a lot quicker, couldn't I? Sorry.
Oh, thanks for the background information.
Yeah, but there's some great new low carbon concretes out there. In fact, there was one. I've still not checked the paper. Always got to be careful, where they were claiming that it absorbs more carbon than it actually produces, or it's about a 90% reduction, even including the manufacture of the cement. So when it cures, it absorbs a huge amount of carbon. But I've not checked that as it's true. But I hope it's true. That's a step change.
Sounds amazing, but also ambitious.
Yeah, I mean, we're going to build with concrete no matter what. We've got to find some solutions. Isn't concrete about 7% of our CO2 footprint as a species? It's something of that order, which puts it number 3 on the planet after China and America. I mean, I know they use concrete as well, so it's actually a false comparison, but it is a an enormous question. And you know, the fact that this building is built to last for, I don't know, how long is the world going to last for? It's a, you know, it's a, you know, about 500-600 years. I'd be gutted if the building this building wouldn't last. For the materials have no degradation element to them at all. If you've got concrete buildings in Rome that are around 2,000 years afterwards, then I don't see why I can't, you know. So if I've got embodied, yeah, there's a lot of carbon in the manufacture of this. But if you're looking at 500 to 1,000 year life of the building, then I could kind of claim, since it's got no energy input, that you know, overall it can. But it's a long game. It's a long game. It really is. And sorry, what?
I'm gonna.
Oh right, the research. I've got a question here. Let's have a look. It's Steve Hetherington at Sheffield Hallam University. He's a materials specialist there. Him and Professor Liz Laycock do a lot on materials, concrete, and structural integrity. Professor Laycock's work is on is at the other end. She does more cathedrals and old buildings and how to extend their lifetime. And Steve is more about the new stuff. So yeah, get in touch with him. He's forgotten more about that sort of stuff than I know.
With Jordan's question, I've got a slightly similar one, which you could maybe answer both of them at once, which was about like the most applicable parts of your like house to the sort of mass housing market.
The mass housing market, you wouldn't go with a circle. You would just lay them out very much like the Hockington. I don't need to create the mass housing. The Hockington houses are terraced houses that could be laid out in strings, zero heating, super energy efficient, and they're really interesting in that the north side of the house is covered in a soil bund, so you could put the next row of houses very close behind the row in front, and you look out over a slightly rising garden. You don't extend your garden onto the top of their house, that would be awful, but you can go halfway. And what it means is you can bring those houses very close together. So the mass house version of this was designed 20 years ago. I just took it to a sort of like a high end, and it's the resilience thing. They're not flood proof because they're bungalows, but you could come in with elements of this. But like I said, I'm really twitchy about flat wall and flood resilience. But in terms of wind resilience and temperature resilience, absolutely, that's already done. You know, have a look at the Hockington research, Hockington Housing Project. Check out their website. Yes, I do. I do say that if it doesn't cost significantly more, then I don't see why you wouldn't design houses as autonomous and as resilient as we can build them. I just think that the pride in our construction has just been lost over recent years, lost for purposes of profit, I imagine. But the idea that you could design something that is stable and safe, no matter what is coming our way, just to me seems like the way buildings should be built, if you can, especially since it doesn't actually cost a great deal more or any more to build them like this. They just look different. Looks a bit odd. I can't deny a roundhouse. My wife's first comment on that was like, we can't get any furniture in that then, can we? With the curved walls, what the are you doing there? And it's like, all the internal walls are straight, man. They're all straight. We can put straight things in there. It's just the outer wall. And actually, at a 12-meter diameter curve, it isn't as steep a curve as you'd imagine. It doesn't take a great deal to straighten that, you know, internally. Oh, nice. That is a beautiful idea. Carbon fiber and reinforced polymers. That'll even knock concrete into touch in terms of the strength. You know, it's. I have to say that I did, at the end of the day, I had to do a costing. I have a very limited. I have to spend every penny I've ever earned to build this and sell my current house and everything, you know, to have a chance of funding this, unless I can get some kind of, if I could, the thing is, if I could build a house like this down in Cornwall, I could sell it for 7 figures relatively easily. And the really interesting thing, since it's an autonomous house, you could build it without services connection. And it's a lot easier to get planning permission on plots of land anywhere in the UK if you've got no services, because the council think that you won't be able to build anything. And yeah, we've already engineered our way out of that nominal challenge. Yes, you'd have to put batteries in rather than grid connected. So this house is, I forgot to mention that, this house would be grid connected. And the reason for that is, by my calculations, the solar and wind turbine should allow me to power my house completely and make about 5k a year profit selling electricity. So not a massive amount, not enough to live on, but certainly enough to do all the maintenance and food and water maintenance elements to it. So I'll make just enough profit to get all my seeds, all my fish, and all the pumps and everything that I'm going to need replacing on a 3 to 5 year basis, as well as a money in the bank to replace my wind turbine sort of 15, 20 years in the future. Right, okay. So Dominic, is it perceived losses associated with corners are less applicable when you put in these houses? Yeah, well, indeed. So terraced houses don't lose. That's why terraced houses are so energy efficient in flats. So yeah, when you've got only one front elevation on a block of flats, they're loads more efficient, right? So the biometrics and the biomimicry. Well, the whole thing about this was around the biophilic building idea. That's why, you know, the food production is embedded within the building. I didn't get a chance to really talk about that, but in my head, the building is like a living thing. It would probably take about 2 years before I got it balanced between the heating the floor and water capture, food production, rainwater collection, clarity, you know, and it would be a slow process. But once in balance, that whole idea of an organic, it would function like a living thing with capturing rainwater and everything. And I mean, it can't capture carbon out of the air, but the plants and everything would. And the land behind this plot is an ongoing plan for I want to grow coppicing and food production around that. It's a very exposed site, so the plan was to coppice around the edge of it very deeply, and then have a food production. So the whole thing, inside and out, as well as the wetland water treatment, which is what I was planning to do. So this uses a wetland idea where you use a cochlea, and you take your black water and run it through a cochlea, which takes about a year to run through the reed bed, and then that's released. But in there you've got sort of like the biodiversity elements in there. Will you maintain the hydroponic fish tanks yourself? Yeah, the fish type was tilapia. It has to be tilapia. So those of you that are unfamiliar with this as a fish, it's a African Nile fish, I think. It lives in total darkness at the bottom of the Nile. It is super tough. You really, killing them, you have to really try. And they're really good at high temperatures. So when the water temperature of the pool gets really high up, they actually become more active. And tilapia will eat almost anything, grass cuttings, as well as a small amount of meat. So they taste great as well, and their skin is actually good enough to make leather out of as well. I'm not going into fish leather making though, but you can. I've seen it done. So tilapia would be my primary one. I would have preferred to have kept with a UK-based fish, but they are really challenging and they don't taste. British freshwater fish, damn, they don't taste as good as tilapia. I know, and they're not as thermally comfortable. You'd kill them with the environment that I'm planning on creating around the freshwater pool and the growing area. So, you know, you have to go. And ideally, I would want to go with black soldier flies as well, if I could get a breeding population going. They sound really scary, but they're not. They don't even have mouth parts when they're adults. They don't bite or anything. I don't know why they're called black soldier flies, but they'll, as larvae, they'll consume absolutely anything, and they'll recycle almost any organic waste into food for the fish, which is little maggots, which they just, well, they're not that little actually, but that's more blue sky. I need another lecture for the food production and water production. Not lecture, I need another chat. Yeah, so hopefully you got that, the idea of the wastewater. So this wetland treatment system, if you have a look at the Hockington system, I'm just stealing theirs. Theirs is, I think theirs is it 30 or 50 square meters, and that will do black water treatment for 120 people. The one that I'm doing is a tenth of that, so it's for 12 people. So that was my so it's 12 people, which is way beyond, you know, the 5 or 6 that this one was dealing with. I didn't get a chance to talk about it, but you've got the roundhouse, the swimming pool, and then there's actually a retirement annex at the other end, which is where I and my wife had planned to move to. Oh, well done, thank you, Nathan. I plan to move that to there when we become perhaps less mobile. That's a really small bungalow where I can just potter around, and no doubt my children will move me out to take the 4-bedroom house with the but I still get access to the swimming pool from there, because, you know, the houses are either side of the swimming pool. But that's a much simpler design there. But I didn't, you can see on the plans when you have a look at the lecture slides, Nathan's got my slides, that the layout, that you've got this very small sort of 2-room bungalow with an elevated bedroom, but you don't have to use that. It's just a way of adding more space, because the design of because it's an asymmetrical design, so that it's big, it's higher at the front, and it shallows down to about 1.5 meters at the back, so it's very shallow, and it's designed for the low sun of the winter into the building or the swimming pool area, so you maximize it. And since the swimming pool directly abuts the back wall, you don't really notice the fact that the roof comes down over the pool. So, you know, it's everything, I think, you know, sort of works towards making it a really high quality environment. I'm not sort of saying this is not a sackcloth and ashes kind of lifestyle. This is a proof that you can actually put £1 million house that is fully autonomous, simple to maintain, I think looks quite nice, and, you know, is of high value and high quality of environment. That was what I was going for. And then the idea is you take bits of it out of there once I've proved it all together, and build those elements sort of separately, like the flood protection or the wind thingy, the circular house element, the concrete roof, the rainwater collection, the sewage treatment, the conservatory with integrated solar, the roof mounted wind turbine. All of these things are individually, they've already been done. It was just the idea of pulling it together, and it turns out it's not that expensive in the scheme of things. These are quite simple elements, but you can always spend a lot more, you know. Self-build, damn, you can spend 40 grand on a bathroom, can't you? My bathroom, my entire internals is done on 40k. It's a very, so I've gone quite Spartan once I built how I'm doing it is, my wife's an interior designer, and so you can claim the VAT once on a self-build. So I'm building the house, claiming the VAT, and then my wife gets the VAT payment to do the interiors, and that's how we're doing it. So yeah, so she's rubbing her hands together with this fund, and then I don't have to deal with all the interior stuff, which honestly it just doesn't interest me that much. But it's nice when a woman certainly when my wife has designed the interior, so it'll look great. But I don't have that. That's not part of me. So we're a team. What can I say? I designed the house. She makes it look beautiful. That's the thing. And then I get to sell it. You know, that's my plan, is that, you know, parts of this, and there's a version of this that doesn't have a swimming pool adjacent, but has a swimming pool in the basement. So there's a 3-story version of this. where you have, because the pool will fit in the footprint of the house, but I couldn't do it here because I told you there's granite below, and it would just be too expensive to put the swimming pool below. It's not as flood resilient because you've got a whole story and a half there to work with, but you know, it'll take that. But you know, these are things to maybe talk about. Please feel free to get in touch or whatever. I'll bore the ears off anybody who wants to talk about this. You know, and that's me. How we're done. So I'll shut up now, Nathan.
Well, that was really interesting. Thanks, and thanks to everyone who asked such great questions as well. Coming up to 7 now, so unless there are any final questions, start wrapping up. So yeah, thanks again for great talk. I'll give a brief plug for our event talk next week, which is by a guy called Nile Fish, who designed he's designed like a hand cranked washing machine that, and it's started this charity called the Washing Machine Project. Really cool guy, really cool ideas, and they're sort of having a real impact in, I think most of their activities are in India and Iraq at the moment. So I'll put the link to that in the chat, and if anyone has any questions about EWB or wants to be put in contact with John, our email's in the chat as well. So yeah, thanks for attending, everyone. I'll put the recording up on our website tonight or tomorrow morning, so it'll be up there if anyone wants it. Bye. You're on mute, John.
Sorry, I'm just saying goodbye, and thanks for giving me the opportunity to talk about my dreams and my passions. So yeah, putting up with me. But yeah, so if anybody wants a building consultant for building their own self-build autonomous house, feel free to get in touch. Feel free to get in touch. I'd rather do that than marking scripts, that's for sure. Okay, Nathan, I'm heading off then. Thanks. Bye.
Thanks, John.